Welcome to part 3 of a personal history of Unix, Linux files and processes, and we're going to jump right into processes. So let me excuse myself here and bring up processes. So Linux is a operating system that allows multiple things to occur at the same time, basically. Even with a single processor, it's a multi-threading. In other words, you can have a browser in the background along with, let's say, a document that you're viewing. In fact, if you look at my terminal, I've got the system monitor running. I've got the command line running, I've got a terminal running, I've got multiple browsers up and running, I've got multiple documents, I've got this cheesy webcam that's running, and then there are other things that I can start up and get running in the background. All of these occur at the same time. Well, I say at the same time, but in reality what's going on is each one has access to resources in the system based on its priority, and the priorities are assigned. But each one of these things that is running is a process. If I go back to look at the system monitor again, look here, I've got IDs on everything. So notice everything that's running is known by an ID, and you see the IDs range in size, and we haven't seen every ID. Here's a process that I want you to become familiar with, systemd. This used to be known as a init, but it is the first process. Now it says it's got ID 1452, but in reality it's a little bit different than that. If I go to the terminal and I do this, grep systemd, you can see that, there it is. It's process 1, systemd. But here, my systemd for the user is 1452, and that's why you see this is the user and the process ID 1452. Let's go back here. So let's discuss processes a little bit, in particular how they're used in the Linux environment. So ID1, which we saw just a moment ago, ID1, there it is, ID1, systemd, is started at boot. Systemd and other distributions, it's init. Here's the fun thing. The PID numbers, these process IDs, PIDs, recycle. Once you get to a certain number, and I can't remember, it may be 64K, something like that, they'll recycle. One should always be systemd. It never recycles. If systemd dies, it will come back. It will actually take the system down, so it's going to come back on a reboot as one anyhow. But once a process terminates, that PID, that process ID for the job, will recycle. It can be reused. It's put back in the pool of available process IDs. So, for instance, let's take a look at this. If I do this, sleep 20, and put that in the background, I see ps-ef, grep, bash, and I want to show you what's going on here. So there's a bash shell that started here. That's the shell one of the shells I'm running. But here's that sleep command. And to show you what's going on here, 1781 is the sleep command, and 1638 is the parent. So, and this is a bit confusing, but Every process has a parent. Every process comes from system D at some point. So we can trace back all of the processes running on the machine back to system D. The other thing to note is the PID I have has an alias. Here it is. It's number 1. If I wanted to kill that job, and if I do that, it will tell me that's already done because that command is completed. If I wanted to kill that job, I could refer to it with that alias, that job 1 in my case. So it also has that system-wide PID. So what is that goofy ps-ef command I just ran? Well, let's take a peek at that. We're going to run ps-ef and pipe the output of that into more. So there it is, the process ID, the parent process ID. Notice init system D is 1. No parent for it. 2, the kernel thread. The ksoft request daemon. The kworker has a parent ID of 2. So 1 and 2 are standalone, and 3, 5, 7, 8, 9 all derive from the kthread daemon. So that's another term that you're going to hear is the word daemon, D-A-E-M-O-N. This kernel thread daemon is running in the background, and it keeps track of processes. So you see the parent ID, or the parent process ID, sitting on this column here. If I do this, that's the parent process ID. And this is the actual process ID. So if it's PID2, which is this kernel thread daemon, you notice that the parent for this ksoft IRQ interrupt request is a 2. The parent for this kernel worker is a 2. So that is this kernel thread daemon is running in the background, and that is controlling a lot of these other processes. So let me go forward a bit, and you can see everything that's running under either 2 or 1. So then we come to other things that are running, and basically you've got an idea that there's quite a bit running around out here. So let's jump into this version of the PS command, the process status. So ps-aux, and we're going to pipe that to the command more. So notice here I've got a process ID, a percent CPU utilization, a percent memory, this virtual size, an RSS, a TTY, a stat, a start, the time, and the command name. So there's a lot that's running out there, but not a lot that's using memory and other things. However, if we go back to this, which is nothing more than the basic ps-aux, if we look at memory, Firefox is chewing up a gigabyte of memory. Let's see how that looks. There it is, 2.3 gig of memory in use at the moment. The processes, so who's using up the CPU utilization? Well, that goofy webcam is tying up 24-25% of the CPU on a regular basis. Here, this little background switcher program that actually switches the background that's displayed on the screen is chewing up some CPU cycles. So let's move forward. Here's an interesting command called a ps3, and it shows you the linkage between various processes. So let's run that for grins. ps3. And there is a visual representation of all the processes that are running on this machine. So let me do this. System D, process 1. There's a modem manager, a network manager, accounts, a Getty, Bluetooth HD running, which I don't have any Bluetooth running at the moment, as you can see, it's just there. LightDM, Xorg, All kinds of things are running in the background on this machine, and you can see how they interrelate based on this ps3 command. Um, this one's interesting. It's the logical volume manager. So let's jump back out of that, jump into this. So that gives you an idea of how these processes are attached to each other. Here's another one. This is what we talked about just a little bit ago when I did this sleep command, and I'm going to do that again. Sleep 30, and that's seconds, and I'm going to put that in the background, which is what the ampersand does. So what does it mean to go into the background? Well, if I do a sleep 3, for instance, that's in the foreground. And you can see it took 3 seconds for that process to run before it returned my prompt. If I tell it to do a sleep 30 and put that in the background, it will run that process in the background. It returns a prompt to me immediately, and you can see that it did that. It assigned a process ID, a PID of 18603 to that sleep 30, and it gave me 1. If I want to get rid of that, I can do this. I can do a kill %1. ps-ef grep for sleep. And the only thing that should be running, well, and we see that we get the grep and that we had that sleep 30 terminated, which is what we expected when we did the kill command. It took just a second. You can see we had something back there, a bash-c sleep 3, and that was part of the wk command. So that's interesting. That was running in the background. Okay, so that gives you an idea of that process ID alias, that 1. So let's take a look at that again. Let's do a ps-ef and grep for sleep again. The only thing that should be showing up is the grep command. Well, you see the wk again, so it shows up. That's the background device. Okay, system calls. There are 4 system calls that a process can make. Fork, which creates a duplicate of the calling process. That's what happens when I issued that sleep command. The first thing that happened is it forked a bash. It forked the shell. Await, which is the parent shell going to sleep. In other words, when I ran sleep, it put bash to sleep. The exec is the child calls exec to start the new process. Basically, I've turned over to the child, that sleep command, the authority to run. And you saw that with that sleep 3, it ran in the background. Exit, when the child finishes, it sends a signal. The parent wakes up, and the child waits for the parental acceptance of the child's exit. So basically, the process says, I'm ready to exit, wakes up the process that spawned it, and then that process says the process that woke it up can die, can go away. So the child will exit. So is there a way to end the process? Well, sure. You can do that kill command, which is what I showed you earlier. A process that hasn't exited gracefully, you can kill using a number of tools. For instance, if I do this sleep 30 again, there it is. I want to do a Control Z. That'll stop it, and I can do a kill %1. That'll kill it. So wait a minute, it says it stopped. Kill -9. How's that? %1. So it still stopped, it says. Okay. Let's take a look at it again. Here we go. ps-ef grep for sleep. It's terminated. Okay. The Control C got rid of it. Kill -9 should have gotten rid of it also. However, kill command can end a process. The sure way is the kill -9. Okay, files. and we're going to go through this and processes again in class. So I know it's a bit confusing. We'll go over it again. The file structure. Let me go back up to the terminal here. I want to do this. The file structure in Unix is kind of interesting. File boundaries are known with a slash. So you get that slash. The first file is the root directory, basically. So where am I? I'm at root. That's the first file boundary. What's in root? Well, binaries, the boot devices, the boot programs, devices, the etc is additional stuff, the home, which is where user files are kept, media, which is anything that's attached to the machine like USB devices, processes, opt, which is optional, root, run, sbin, server, user. User very often has programs in it. And then there's a couple of interesting files here, vmlinux, vmlinux.old, and also temp. Let's do an ls-l on these. Notice temp has a little interesting file permission sitting on it that we'll talk about later. So this is how files laid out. It's a hierarchical structure. File boundaries are noted with the slash. In other words, the directory structure it starts with a slash, the name of the directory, another slash which says that that's a directory boundary, and another name of either the file or a continuing directory structure. So, file names, what can they be? Well, to be honest with you, they can be just a little bit of anything. And file names in the Unix environment don't have to have a suffix that denotes what that file type is, as opposed to DOS that used to have that. Also, it's very important to understand this. Unix and Linux are case sensitive. Documents does not equal documents. So lowercase d, uppercase d are different files or different directory structures. What is the maximum file size? You know, the name. So how long can the name be? Well, you can find that out with the getConf name underbar max. There's a configuration parameter called getConf. File name and contents. What's a file? Well, just zeros and ones. It's not important. Suffix is not required in Linux, but some applications expect a suffix. So there are some applications that run that may not be able to deal with a file that doesn't have a suffix. For instance, photography tools. The name of a file cannot have a slash in it, since Unix interprets a slash as a directory boundary. You can escape the slash, but in reality, you don't want a file name with a slash in it. The application called will determine if it can read and display a file. We're going to talk about this later, but index nodes is metadata. The inode is a piece of metadata that contains data about the data. In reality, when we look at, if I go to my directory, I'm going to go back here, I'm going to cd to nothing, which actually takes me to myself. This process that you see in front of you, all of these directories in the one file called gears tilde, are metadata. The actual files, those aren't the files themselves. Those are pointers to the file. The data in the inodes is basically information about where to find the file, and we'll talk about that more later. So there's a stat command. Let me run that against this gears. Stat gears tilde. Tells me what the file is. It's 47. It's a device file. It's an inode. It gives me the inode number. It just says it's the file name is gears. The size is 47. The blocks are 8. So what is gears? Would you believe? It's just a URL. That's all it is. It's a regular file. In this case, that file consists of nothing more than a URL. So, if I run the command file, let's do this. File on gears. It's ASCII text, which is exactly what you expect it to be. So, How do I get around in the file system? And I've shown you a little bit of this. So if I do this, cd to slash, which is, remember, a slash is the directory boundary. That takes me back to root. That's the start of the file system. If I do cd dot dot, let me cd back to myself. So where am I? I'm there. If I do a cd dot dot, where am I? I'm one directory up. So dot dot changes up one directory. I can use that cd command or a cd tilde to take me back to myself. If I do a cd back to slash and do a cd, I'm back to myself. Okay, not bad. Here's an odd duck one. You can cd to dot slash and the current directory name from the current directory. So if I look at this, if I do an ls and there I have the desktop, if I do a cd slash desktop, that takes me to desktop. That's an odd implementation, but we'll talk about that more later. So basically, there's the ls command, which lists the directories. If I do an I'm going to clear the screen here. If I do an ls-l, nothing's in my desktop. So if I cd dot dot, which takes me up one directory, now I'm home. If I do an ls-l, here's a list of what is there. And you notice that I have all of this information on the side. I have the owner and the group and the size, when it was created, and the name of the directory. This D here tells me it's a directory, and the RWX, RWX, R-X tell me the permissions of the file. So we're going to go further into this a little bit. This talks about symbolic links. There is a way to link one file to another file. In other words, I give it two names, but it's only one file, and I create a symbolic link which takes me to there. And here you can see the L, which is telling us that that test1 is a symbolic link to a file called how to name this. Permissions are granted for Unix files, for access to Unix files. And in the Unix Linux environment, pretty much everything is a file. Permissions are granted for user, group, and other. Permissions are assigned based on the user's UMask, in other words, the user mask when the file directory is created. There are read permissions, write permissions, and execute permissions. The read, write, execute for the user, read, write, execute for group, and read, write, execute for others. There are some extra tidbits that go with this, though. Sticky bits and run as are examples, and we'll talk about those later. For instance, this command called su, which is super user, has an S. This runs effectively as root. In other words, when you type the su command, you're running that command as root. It also prompts you to give the root password in order to make that work. But that's another piece that we'll talk about later. You can manipulate file permissions using the chmod command, and we'll do that in class. The variations of chmod are, you can do RWX, or you can do the octal, which is 777, G plus W, group plus write. So the change own command, which is different than the change modifications, so the modifications to the permissions on the file. The change own actually change the ownership of the file. So if I own a file and want to give you ownership of the file, I can issue the change own command and specify your username, and you would then own the file. So how do we manipulate files? And we're going to do this quite a bit during class. That make directory, copy a file and give it a new name, copy a file to a new location, rename a file in Unix, which is a move command, remove a file, which is the rm command. And we're going to do a lot of this in the week 2 classroom. Man pages. Read the manual. Man pages exist for every command available in Unix, basically. If you create a new command, you should also create a man page for it. Man pages tell you how to use the command. It tells you how to use the options for the command. We are going to use man pages quite a bit, and your projects will have you using man pages. Most commands in the Unix environment can be found in a bin directory or binary directory. When you type a command name, the shell tries to find it in one of the locations found in what is known as a path. And to see what your path is, you can do this. You can echo $path. And that is asking the system to tell me what is included in the variable called path. That's what the $sign tells it. It says get the contents of path. And this shows me where the system is going to search when I type a command. This tells me what files it's going to, or what directories it's going to look in for a command when I type a command name. So the output of path we just saw. Again, everything that we've talked about with processes and paths and files we will talk about in greater detail in class, and we will get our fingers on it. It is absolutely important that you learn how to create files, transit around in the Unix file system, how you can change permissions on files, how you can change ownerships on files, how you can start and stop processes. This is all fundamental. If you don't get this, you won't get anything. So, in the grand scheme of things, that's it for week 2. And I'll see you in class, and we'll jump into this in greater detail. Thanks.